So in this section, we're dealing with direct variation. And direct variation equations all have this form. They look like y equals kx. And k is just a number, okay? Y and x are variables. Y and x are always variables. But k is just a number, so it could be like 3 or -2 or 4/5 or whatever. Whatever that number is what that number is, okay? So k is called the constant of variation. Sometimes we're going to have to figure out what that number is. Sometimes we won't have to figure out what that number is. It's just given to us. But it's always just going to be a number. So in the graphs and these examples at the bottom of the page here that I have, what is the constant of variation? We know that it's k. We're going to try to figure it out. So in the equation that we have here, what is the constant of variation? What is the... Yeah, it's -4. So k is -4. We just read it right off the equation. Okay? And how about the other equation? What is the constant of variation there? K is 1/2, yeah. All right, it's just the number that's attached to x. That's it. In a direct variation equation, y equals kx. K is the number that's attached to x. That's it. Okay? Now, the second question is, what is the slope of the line? So in section 1, we learned how to take a look at a graph and figure out what the slope of the line is. How do we do that? Yeah, we look at rise over run. So we need to pick out a couple of easy points on the graph. So we find an easy point. Here's one right here. And then here's another one right here, like right at the origin. And then we do rise over run. And remember how I taught you how to do that. We're going to read it like a book. So we start at the left point and we move our way to the right point. Okay? So the left point is the one that's up high. And we're going to rise which way? Up or down? Down. So that makes -4. And then we run how far? 1. So we have -4 over 1. So our slope is what? -4. Okay, and what letter do we use for slope? M. And we don't know why we use the letter M. We're just told that we use the letter M, so that's what we do. Okay? And how about this other example? We need to pick out a couple of easy points. I see one right here at the origin. Do we see another one? Give me the ordered pair. Okay, -2, -1 is one. Is there another one? Where? +2, +1. Good. Okay, so what is the slope here? Pick a left point and move to a right point. Up 1, so that's a rise of 1, and a run of 2. So on the bottom we have 2. 1/2 is the slope. So I would call that m equals 1/2. What do you notice between these two examples? The constant of variation and the slope are the same thing. Okay? So in these equations, y equals kx, instead of the letter k, we could use the letter m instead. So y equals kx, we could say y equals mx instead and have the exact same thing. Okay? So k is the slope. M is the slope also. All right? But in this section, we're going to be using the letter k. I'm actually just giving you a little bit of like advanced knowledge. In the next section, we'll be dealing with y equals mx. In this section, we're saying y equals kx. Okay? All right. So let's continue. So some important notes about direct variation. If you look back at those two problems that we just did, if you make an observation about what both of those graphs do, when one is going up and the other one is going down, but what do both of those graphs do? Yeah? They both go through the origin. Okay? So if I look at these important notes about direct variation, every direct variation equation goes through the origin. Every single one. So if you have y equals kx, if you have an equation that is of this form, y equals some number times x, the graph of that equation will automatically go through the origin. Okay, that's actually very important. The constant of variation k is the same as the slope. is the same as, can be written as an equal sign. So k equals m is the same as saying the constant of variation is the same as the slope. Okay? That means that y equals kx is the same as writing y equals mx, where m is the slope of the line. We know that m is our symbol for slope. So to graph these, it's actually pretty easy to do. What you do is you plot the point 0, 0. So the origin is one of the points on our line. And then you use the slope to get the second point. The slope is the same as the constant of variation. It's the number that's attached to the x. It tells you a rise over run. So you just do a rise, and then you run, and then you put a dot. You do a rise and a run, and you put another dot. A rise and a run, you put another dot. Now you got a whole bunch of dots, you can draw a line. You'll run 1 if there's no fraction, okay? If you see a fraction like maybe 2/3, then you'll rise 2 and you'll run 3, okay? So like graph y equals negative 3x. Well, so that's negative 3, but we're going to put that negative 3 over 1 so that we see that run of 1. So yeah, we're going to plot our origin point because we know that this graph is going to go through the origin because it's a direct variation situation. So that means that we're always going to go through the origin. And then we're going to graph our slope. We'll use the slope to get more points. So we have a rise of negative 3. So we're going to go which way? From that point that we just put on there, we're going to go down 3 and then over which way? To the right 1. We're going to run to the right 1. Okay, now do it again. Down 3, right 1. And actually in your head, say right 1. Okay, don't just say over. Tell yourself which way. Okay, the negative sign can apply to the rise. We can go up or down. The negative sign can apply to the run. We can go left or right. But it can never apply to both. Okay, you can't use it on both. So what I'm going to tell you to do is always apply it to the up or down so that you're always going to run to the right. All right. Now, we only have 3 dots on here. I like having more dots. So what we're going to do, we applied the negative sign to the rise. We went down 3, right 1. But if we apply the negative sign to the run instead, we go back to the beginning, back to the origin. And now if I apply the negative sign to the run, so it's like we're doing this now. Instead of negative 3, positive 1, we have positive 3, negative 1. Then we would rise 3 up and run left 1. Okay? So it's like we reversed it. Instead of down 3, right 1, we're going up 3, left 1. So then do it again, up 3, left 1. And now we have more dots. More dots is better, always. Now you're going to need rulers or something straight at least, a driver's license or your mom's credit card or something to draw these lines. Okay? Straight lines. Not sketches, not your book, not a folder, not your Chromebook, okay? Something, a straight edge is needed for this, okay? So I will have an impossible time drawing straight edges on these boards. So I'm going to use my ruler. Yeah, my ruler, I'm going to cheat here. And I'm going to sketch it on here the best that I can. But it needs to be all the way through the grid. And you need to draw arrows on the ends. Those are the rules. Because the line actually extends forever in both directions. So we represent that by showing the line drawn all the way through the grid that we have. And then we put arrows on the ends. So a straight edge. And then arrows on the ends. So let's take a look at the second one. Y equals 2/3 x. What do? Plot a dot at the origin. Because it's a direct variation equation. We know we're going to go through the origin. Now what? Rise of 2. So we go up 2. And then we go to the right 3. And we put our dot. And then technically 2 dots is all you need to draw a line. But we want to be more accurate than just 2 dots. So we do it again. Up 2, right 3, put a dot. Now we reverse it. Okay, we were going up 2, right 3. So we go back to the beginning. We reverse the directions. Then we go down 2, left 3, put a dot. Down 2, left 3, put a dot. Now we draw our line with a straight edge all the way through the grid and arrows on the ends. See, I kind of missed there with my line tool. I know. If I had my old board, it would be good. Because I could actually take a ruler and put it on this board, but I can't do that with this board. Which makes me very disappointed. Okay, that's the idea, all right? You guys, when you draw your lines, make sure that they're nice and lined up with the dots that you drew. And draw a straight line. If it's not a straight line, then it's not a line. That's wrong. If you look at these two graphs, what was the sign of the slope in the one on the left? Negative. And what way was our line going when we graphed it? As we read it from left to right, it's going down, right? What was the sign of our slope in the one on the right? Positive. And what way was our line going? It was going up. Again, this is the best way to check, and it takes like half a second to look at the sign of your slope and the direction that your line was going to make sure that at least you got that much right, okay? As we go on, like when we get into the next section, I'm going to give you guys a little bit more information on checking to make sure that your line is right when you graph it, so that by the time you're done, you can actually really graph these in your head, and when you get it on paper, you're going to know whether you're right or not just by looking at it, okay? Really, you need to be good at doing that so that you're not getting things wrong, okay? You should be able to graph 20 problems in a row by the time we're done with this chapter and just look at your answer and know that it's right on all 20 problems. That's the goal. Okay, so now graph these two. Y equals negative 3/4 x. What do? We're going to put the dot on the origin, but tell me something about this line by the time we're done. It's going to go through the origin, and it's going to be going down as we read it from left to right. Okay, good. So we're on our origin, down 3, which way? Right 4. Put a dot. Now, if I go down 3, right 4, I don't have another spot for a dot, right? Does that mean I'm going to draw a line in there, draw more grid lines? No, don't do that, okay? That's like 4th grade stuff. We don't do that here. So I'm just going to reverse it now. Go back to the origin, go which way? Up 3 and then left 4. And that's as good as I'm going to get. I'm only going to get 3 dots this time, and that's fine. So now draw your line with those 3 dots. Line up your ruler really good and draw the line. Now I got to do the best I can here. I don't know, we'll see. See how I do. Pretty terrible. Be quiet. Someday I'll try to get better. Do the best I can with what I got. So let's take a look at the last one now. What do? Tell me something about this line. It's going to be going up when we're done. And what else? It goes through the origin because it's direct variation. So where do we start? Put a dot on the origin and then up to and then to the right one. And then, yeah, do it a bunch more times. Up to right 1 a bunch of times. Okay, I'm out of room. Now what? Down to, reverse it. Down to left 1 a bunch of times. Down to left 1, down to left 1 until you're out of room. It should look like a line when you're done. And it does. So now what? Okay, draw the line. Got your mom's credit card. You draw the line. Look at how good I did on that one. You check it real quick to make sure it is going up as you read it from left to right. The slope is positive, so you think you did a pretty good job. Okay? And then, like I said, down the road, I'm going to give you a couple more tips to help you make sure that you know that you're right as well. It has to do with how big the slope is compared to how steep your line is. All right, so if an equation can be written in the form y equals kx, like we've been working with so far, it represents direct variation. So the question is now, do these equations represent direct variation? So when you get questions like this, what they're really asking you to do is solve for y. Put it in y equals form. And if you wind up with an equation that looks like y equals kx, then the answer is yeah, it's direct variation. Okay? If it doesn't look like y equals kx exactly, if it has other stuff hanging out, or if it just doesn't look like y equals a number times x, then the answer is no. All right? So let's take a look at the first one. 7y equals 2x. Obviously, it's not just y equals right now. Okay? We want just y equals. So how do I get y equals? Divide by 7. So now I have y equals, like I wanted, equals what? Yeah, 2/7 x. We could write 2x over 7, but that's the same as 2/7 x. We're not graphing it, though. We're just trying to say, is this direct variation? We could graph anything. We can graph any equation that there is. Okay? All we're trying to do right now is say, is this direct variation? Does this look like y equals kx? On number times x. The answer is yes. Okay? So now it says, if so, find the constant of variation. So you said, yeah, that's direct variation. What is the constant of variation? It's just 2/7. So you're going to say k equals 2/7. So there's actually two answers here because it was direct variation. Okay? If it's not direct variation, and the answer is just no, and you move on. Okay? So let's take a look at the one to the right. 3y plus 4x equals 8. We want to solve for y. What do? First thing you do is subtract the 4x from both sides. So what do we have? 3y equals negative 4x. We subtracted 4x from both sides. Plus 8. Okay, we haven't solved for y yet, though. So then what would we do? Divide by 3. This is good practice. We're going to be doing this in the next section. So divide every term individually by 3. What do we get? Y equals negative 4/3 x plus, and we can leave it 8/3. That's fine. So there's fractions there. Big deal. Okay? Don't throw up all over yourself just because there's fractions. It's not that bad. Is this direct variation? No. So you just say no. Circle it. Move on. There's nothing more to do. The next one. 4x plus 5y equals 0. We got to get the y by itself. So we subtract 4x from both sides. Okay, 5y equals, thank you, negative 4x. And then? Yep, divide both sides by 5. What do we get? Negative 4/5 x. Is that direct variation? Yeah. So you're going to say yes. And we also have to say what now? K equals that number, negative 4/5. All right. What do you think about that last one? Would I multiply by 6? What's the issue? Yeah, right now we have 6 times y, so we're going to undo that by dividing by 6, right? Okay. So if I divide by 6, though, that gives me something weird on the other side. So rather than dividing by 6, I can multiply by the reciprocal. Good. So we're going to multiply both sides by 1/6. That makes the math a little bit easier to deal with. So on the right-hand side, I get what? On the right. On the right. On the right. Get y. That was the whole point. Okay, now on the left. 3/4 times 1/6. 3/24. Okay. So what's 3/24? 1/8, nice. 1/8 x. Is that direct variation? Yes. So therefore k equals what? 1/8. That's the idea. If you got extra junk hanging off on the side, like that 8/3 on that second problem, no, that's not direct variation, okay? If you can get it looking like y equals kx with no other stuff hanging over the side, then it is direct variation, and that k is just the number attached to the x. All right, so these problems are the classic types of direct variation problems that you're going to see. Suppose y varies directly as x, and y equals 72 when x equals 8. Okay? When you see a problem that sets up like that, as soon as you see this phrase right here, varies directly, you have to think y equals kx. All right? That phrase means y equals kx. That has to pop into your head. Okay? Now, it says write a direct variation equation that relates x and y. Well, y equals kx is your direct variation equation that relates x and y. The only thing you don't know is k. Now, the information that they gave you, y is 72 when x is 8, is how you're going to figure out k. Okay? They told you x and y. What you do is you plug those two numbers in for x and y, and then you can solve for k, and then you know what k is. All right? So, we have 72 for y. It's just 72 gets plugged in for y. You substitute it in. Equals k times, and then x is 8. Like that. So then you divide both sides by 8. What is 72 divided by 8? 9. So we have k is 9. So now we know what k is, which means our direct variation equation is y equals 9x. Okay? We use the information that they gave us to figure out what k is so that we know what our direct variation equation is. Y equals 9x. And now that we know that, we can find anything that they want to have us find. So they have in number 2, use the direct variation equation to find y when x is 3. Or in number 3, they have use the direct variation equation to find x when y is 45. Great. We can find anything they want us to find. Okay? It's just a matter of plugging in the number that they give us and finding the other number that we don't know. Okay? So in number 2, use the direct variation equation to find y when x is 3. Okay. Y equals 9 times x is 3, so plug in 3. 3 times 9 is 27 is your answer. And then do the other one. Use the direct variation equation to find x when y is 45. Okay, so we plug 45 in for y, but we use the same equation. So y is 45 now. 45 equals 9x. So solve for x. What do we do? Divide both sides by 9. So 45 divided by 9 is 5. 5 equals x. And you're done. These types of problems show up all the time with direct variation, okay? The key is when you see varies directly, you have to think y equals kx. And then you just take the information they give you, plug it in, find out what k is, and then you can do whatever they want you to do. Okay? We have another example that's just like this. Suppose y varies directly as x and y is 36 when x is 9. First thing they want you to do is write a direct variation equation that relates x and y. So what do we do? We got to remember y equals kx first, and then you plug in your stuff, and you're right. 36 equals k times 9. So now what? Divide by 9. What do we get? 4 equals k. So what does that tell us? 4x. Yep. There's your answer. Now you can do whatever it is they want you to do. So use the direct variation equation to find y when x is 3. So what am I going to write? Four times 3 is? Okay, that was done. And then the third one there, use the direct variation equation to find x when y is 48. What are we going to do? Four x. Okay, and then? Yep. 12 equals x. Done. Okay? So those hopefully aren't so bad. There's a few problems like that on the homework. All right, the distance a jet travels varies directly as the number of hours it flies. In that sentence, what was the most important thing that you needed to pick up on? Varies directly. Yep. As soon as you see this phrase right here, what do you need to think? Y equals kx. A jet traveled 3,420 miles in 6 hours. So now this is going to be kind of tricky because with the varies directly stuff that we did before, we were told y and x, right? So it was not a problem to think of what was plugged into what. But here in this story problem, we don't know what's y and we don't know what's x. Think so? Normally, x is the independent variable, okay? So here, what is the independent variable? What are the variables here? Miles traveled and hours flown, isn't it? So the distance and then hours that it flies. What do we control? We control the amount of time that we're in the air, don't we? Yeah. And then the amount of time we're in the air determines how far we fly. Okay? All right. So the hours it flies is the independent variable. This is x. The distance that we flew is y. And if you think about it, the language of direct variation on a normal problem says y varies directly with x. Okay? And what we just wrote here is y varies directly with x. So that language there actually makes sense with the way that the variables are written. Okay, so write a direct variation equation for the situation. What are we going to do? $34.20. Okay. Yep. K times 6. Okay, now what? Yeah, divide both sides by 6. Okay, what is 34.20 divided by 6? Nobody knows. It's going to take us forever to find that out. Nobody ever taught you how to divide. Long division is lost. There's no device that exists. 570. Okay, so the equation, it wants the equation. Write a direct variation equation. So what is the equation? Okay. Now that's an answer. We're going to put a box around it because it was specifically asked for. Now number 2, graph the equation. Okay, so we can do that. Origin goes where? Origin is always 0, 0, but it goes in the lower left-hand corner. I know what you meant. We have no negative numbers here. What is on the horizontal axis? X is, but what is that variable? Yeah, hours flown. And that makes what on the vertical axis? The distance traveled. That's miles. Okay. Now what do we got to do? We need scales. So hours flown, what's a good scale going to be there? Yeah, we can go by ones. That's going to be all right. Okay, so I just marked every 5 for a major axis. And, oh, you think 50s? By 50s? I got to go 3,420 miles. One fifty is a terrible scale. I don't want to break it. Here's the problem with breaking. We know 0, 0 is on this graph. And if you break the graph, how are you going to break it and still draw a line? Okay? You cannot break this one. $500s, yeah. So say by 500, and then we're going to mark every 1,000. Okay. I mean, it's not the greatest. It really compressed the graph down, but it's the best we could do. Probably. Okay, now, what's next? Start graphing. How are we going to do that? We're going to go every hour, 570? No. We got a dot at the origin for sure, right? Okay. Oh, we are? We do have a point here. We have 6 hours and 3,420 miles. All you need is 2 dots to draw a graph, right? If you were to take the time to go every hour another 570 up, and then go 570 up over 1, 570 up over 1, 570 up over 1, you're going to wind up using the 3,420 up and 6 over anyway. You're not going to care about all the dots in between because those 2 dots are farther apart, okay? So why don't we just go ahead and graph 3,420 up and 6 over. So here's 6, and then go up to 3,420. It's just short of 3,500. It's right there. Okay? Those 2 dots are already pretty far apart. And 2 dots is really all you need to draw a line. All the dots in between aren't going to do you any better than those 2 dots right there. So now draw your line using those 2 dots. But remember, this plane could fly longer than 6 hours. So although the line won't go any lower than the origin, it can go beyond that dot that we just drew. So my line is going to start at the origin, and it's going to extend out beyond that line that I just drew. So we're going to have an arrow on the end on the right side, but not past the origin. Okay? That is the easy way to draw that line. We take the information that they gave us, plot that point, rather than having to sit there and use the slope over and over. Okay? Okay, now number 3, estimate how long it would take the plane to fly from here to Chicago. Now here is actually here, right? So Grable is about 1,200 miles from Chicago.
570 plus 570 about.
Use our graph, it says, though. Well, actually, it doesn't say that, but let's estimate using our graph. 1,200 miles on our graph is where? Like maybe, so you guys can use your graph, and I'm going to use my graph, and we'll see how we do. So for me, 1,200 miles is sitting right around there, maybe. Okay? So what I'm going to do is we're going to come over to where the graph is, so like right around there. And then I'm going to drop down. And that to me looks like just over 2 hours. Just over 2 hours, 2.1, 2.2 hours, something like that. 2.25 hours, something like that. Okay? So I'm going to say 2 1/4 hours. 2 hours and 15 minutes would be my guess, based on my graph. I don't know what you guys have sitting on your graphs. Okay? Now we can also use the equation, and if we use the equation, all of us should come up with the same answer. Okay? 1,200 miles goes where in the equation? It goes into y. So 1,200 for y equals 570x. Now solve for x. What do we do? Yeah, we got to divide both sides by 570. Okay. Well, we're going to get 2 point something. What is it? You're just making stuff up. 1,200 divided by 570. Enter. 2.10526. So 2.11. But what is 0.11 of an hour? Take the 0.11 and multiply by 60. It's 6 minutes. So it's 2 hours and 6 minutes. So my guess of 2.25 hours, I was a little off. I was off by 9 minutes, but that's okay because I was using my graph and I was just estimating. Okay? 2 hours, 6 minutes would be the flight time. Okay? That's pretty good. All right, one more thing here and then we're done with the section. So from the data in the table, does the y vary directly with x? And then if it does, write an equation for the direct variation. So this is actually easier than it sounds. What you do to check to see if something is direct variation from data in a table is you just compare the ratio of y to x in every single ordered pair that you have. So 6 over 4, 12 over 8, and 15 over 10. Are all of those fractions the same? Do you guys see where I came up with those numbers? Okay, it's just y divided by x every time. Are all of those fractions the same? Just reduce the fractions. What do you get every time? 3 halves. 6/4 reduces to 3 halves. So does 12/8, so does 15/10. These are all the same. They all reduce to 3 halves. Okay? That means this is direct variation. So the answer to the question is, does y vary directly with x? The answer is yes. If it does, write an equation for the direct variation. Well, it could also ask you, what is the constant of variation? Well, guess what the constant of variation is? 3 halves. It's the number that you get every single time. So k is 3 halves. And therefore, because k is 3 halves and this is direct variation, what's the equation for the direct variation? Y equals 3 halves x. Okay? So really, there's 3 answers here. Yes, k is 3 halves, and y equals 3 halves x. Okay? How about B? We don't need to. We just take y divided by x every time. 3.2 divided by -2, 2.4 divided by 1, 1.6 divided by 4. Will these always result in the same answer? How do you know? You don't have to be magical to know.